So what I plan to do today is go back to, actually, let me think. I think this is the first topic of the class. Yeah. So the first thing we did in class was describe exactly the f vectors of the three-dimensional polytopes. And this is something that you guys know very well because it's this cone that we've talked about several times. And those are the conditions for there to exist a three polytope with v vertices, e edges, and f two faces. And you guys know that that's fully understood. And you understand it fully. So let's say, so my plan today is to say more about this, more on f vectors. So we saw that f, e, let's say it like this, f0, f1, f2 is the f vector of a polytope. This we fully understand, right? So the conditions are f0 minus f1 plus f2 equals 2. And then make sure I get the direction of the inequalities right. f0 less than or equal to 2f2 minus 4. And f2 less than or equal to 2f0 minus 4. So in other words, we fully understand three-dimensional f vectors. We understand this in 3D. Okay. And this is something to be proud of. I mean, the proof is not terribly hard, but it requires some serious ideas, and we already discussed all of those ideas, and now we understand this well. But I told you that this is kind of one of the, I mean, this is the dimension 1, 2, and 3 are the only dimensions where we can do this, and I already told you that even in 4 dimensions, this is wide open. We don't really know what the f vectors of 4-dimensional polytopes are, and so that means that in d dimensions it's just even more wide open, right? So in dimension d, in d dimensions, describing f vectors is basically, it seems that it seems hopeless. It just seems to be too difficult of a question. But we do know something. This is something that you might already be aware of, which is that we have a relation like this no matter what the dimension is. This is called Euler's relation. Euler's relation says that if you do f0 minus f1 plus f2 minus f3, etc., all the way up to the dimension, you're going to get 1. Okay. And you might be worried about why here this was equal to 2 and there it's equal to 1. But the reason is that I do this all the way up to dimension d. Okay? And so Euler's relation in 3 dimensions says f0 minus f1 plus f2 minus f3 equals 1. And f3 is 1, right? Because f3 is the one 3-dimensional face of the polytope. So this relation, Euler's relation, holds in any dimension. So let's prove it. But what I'm going to show you is a proof using Erhard theory. And when I finish the proof, you have to tell me what the mistake is. because there's going to be one, not a mistake, but there's going to be one shortcoming, and you have to tell me what it is. Okay. So one thing that we know is that let P be our polytope. So one thing we know is that either let me draw a picture for what I'm about to say. A polytope is going to either a point is in the interior of the polytope, or it's on the boundary. And if it's on the boundary, then either it's on one of the edges or it's one of the vertices. Right? So what I'm saying here is that I can decompose my polytope into the interior of the polytope, the interior of the faces of the different dimensions, and then I'm going to have covered the whole polytope. Okay? So if I take the union over all faces of P, and I take the relative interior of each face, or what we call F0, then this is going to be a disjoint union. Okay? Every point in the polytope is in the interior of exactly one face. And so what this means is that if I want to count lattice points in my polytope, or in some dilate of the polytope, then I just have to sum over all the different faces. So I sum over the faces of P of the number of lattice points in the interior of each face. Right? And this is our notation for that. The lattice points in the interior of that face, and then scaled by T. Okay? But then this is asking for us to use Erhard reciprocity. So that's what we're going to do. And for the rest of the class, I'm going to do this. I'm going to say F less than or equal to P to mean that F is a face of P. And this is familiar because we're talking about the poset of faces. Okay? So in the poset of faces, if F is a face of P, F is less than or equal to P. Okay? So Erhard reciprocity tells us that this is -1 to the dimension of F times the Erhard polynomial evaluated at minus T. Okay? So I have this equality. And this is an equality of polynomials, right? So the left-hand side is the Erhard polynomial of the polytope, and the right-hand side is a bunch of polynomials, but we evaluated minus T, but these are still polynomials and with some signs. Okay? Now what I want to do is say the following. If two polynomials are equal, then they have to be equal coefficient by coefficient, right? So let's take the first coefficient, the coefficient of T to the 0. So sometimes I denote it like this. The coefficient of T to the 0 in the Erhard polynomial is what? You guys remember? It's 1. We proved that the coefficient of the independent coefficient of the Erhard polynomial is always 1. Okay? Now what is it? What is the independent coefficient of this thing? Okay, so that's exactly the catch. That's exactly the catch. So where are we using the P's integral here? All over the place. I'm talking about polynomials. I'm talking about Erhard reciprocity. So I need integral polytope. Okay. So I haven't lied except for that. For this argument to work, I need to assume that my polytope is integral. Okay? But if it is, then it has an error polynomial, and we proved that the error polynomial has independent coefficient 1. Okay? Now, if you plug in minus t in an error polynomial, well, if the independent coefficient is 1, if you plug in minus t, that coefficient is still going to be 1, right? So that's not going to change. So then the coefficient of t to the 0 in the left-hand side is 1. And the coefficient of t to the 0 in the right-hand side is what? It's the summation over f less than or equal to p of minus 1 to the dimension of f times the independent coefficient in this thing, which is 1. Okay. So we're summing over all the faces minus 1 to the dimension of each face. And that means that how many times am I going to get a minus 1 to the k? Well, however many faces of dimension k I have. K from 0 to d. And so I get that on the left-hand side, the independent coefficient is 1. On the right-hand side, the independent coefficient is this, and they're equal. And that proves the Euler relation. Okay. Does that make sense? Do you guys have any questions about it? From here to here? So what I said is I'm going to take the independent coefficient in the right-hand side. So then what I have to do is in each one of these summands, just look at what the independent coefficient of each thing is. And for each one of them is 1. So that means that the independent coefficient of the right-hand side is this thing. And I'm summing over all the different faces of the polytope minus 1 to the dimension. So then if I ask myself, how many times did minus 1 to the k appear? Well, it appeared 1 time for each face whose dimension is k. And I know that I have exactly f sub k faces of dimension k. So that means that this minus 1 to the k is going to appear exactly f sub k times. So that's how it works. Yep.
So whether this relation holds for all polytopes, right, not just integral polytopes?
It would be very strange, right, if somehow Euler's relation depended on having integral coefficients.
So proof exists for the non-integral case?
So what should we do? What should we do to make this work for any polytope and not just for integral polytopes?
Can we just take this? We just say, well, we have the integral polytope, and then when we get in rational, we just move the points around because it won't change the relations.
So. So let me repeat a little bit more slowly what Dito said in 2 steps. So the first step is the following: if Euler's relation is true for integral polytopes, then it's going to be true for rational polytopes. Why is that? Well, if you take a rational polytope, so all the vertices have rational coordinates, that means that just dilate it big enough that it becomes integral, and the number of faces didn't change when you dilated it. So if it's true for rational polytopes, if it's true for integral polytopes, then it's true for rational polytopes. Okay? And then the second part of Dito's argument is, well, if it's true for all rational polytopes, then if you have a polytope that happens to be irrational, just wiggle it a little bit, because the rationals are everywhere. The rationals are dense. So you can just wiggle it a little bit and make it a rational polytope, in a way that maybe you change the angles a little bit, but you didn't change the number of faces of each dimension. Do you buy it? The first part is definitely true. From integral to rational, it's true. The second part, I think, is plausible, but I think it requires proof to say that you can wiggle any polytope to put it into rational coordinates.
It seems like it should be true, but there's so many cases now that our intuition is broken. The third is just the fourth dimension.
So, for example, in the plane, this is clearly true, right? If you take a polygon, then you can wiggle it and make the coordinates rational, and not having trouble. In three-dimensional space, if you think about it hard, it's still true. It turns out this is just false too, and I find it very surprising. But it turns out that there are polytopes that have no realization as a rational polytope. So if you want to realize the polytope geometrically, you need to use irrational numbers. But we never see this because I think the smallest example that I know is 8-dimensional. I don't know, there might be other ones, but there aren't any 2- or 3-dimensional examples, which is what we are used to. Okay? So let me just make this remark here. So we proved it for rational polytopes. But there is a fact which you can decide if you find this fortunate or unfortunate. There exist polytopes that can only be realized with irrational coordinates.
Well, that just means that we can't use the same proof technique. It doesn't mean that Euler's relation is false or is true.
Absolutely. Absolutely. So what this means is that there's no easy way of just extending the proof that we just did to arbitrary polytopes. By the way, this is another interesting topic for a project if you're interested in this kind of thing. You might be mortified by this, or you might be fascinated by this. But this is in Ziegler's book, and you can, in a month, you can understand this, no problem. The fact being that there is a trick for studying. So I think the example is something that has maybe, I think the example has 11 vertices and it's in 8 dimensions. But the thing is that there is a trick for visualizing an 11-dimensional polytope in 8 dimensions as a point configuration in 3 dimensions. So it always, there's just all these tricks to bring your pictures to a dimension that you can manage. And this is one of those examples. So actually, this construction comes from a regular pentagon, and the fact that a regular pentagon innately has a square root of 5 in there. And so from that construction, Perles just lifted it into a higher dimension and proved that that forces the corresponding polytope to have a square root of 5 in it. Okay, so that's a fact. It's an interesting fact. It's a fact that tells us that this proof is not going to work for other polytopes, but this is true for any polytope. Okay? So let me say a couple of words about the proof. One is that you can prove this kind of by induction, and there's kind of tricks to do this. One proof is to basically triangulate and count carefully. But what I should say really is that if you really want to get to the essence of Euler's relation, then you should enroll in a topology class, because this is, I think this is really a theorem in topology and not about polytopes. Okay. And I think I want to just leave it at that. There is a way of making a combinatorial proof. You can read it in the book. But I think if you want to get to the bottom of it, then learn about Euler characteristics, and then this is going to be obvious. Okay. So does that answer your question, Rika? Kind of, I guess. Are you in a topology class? But I mean, there is a proof similar to what I just said. Yeah. Okay, so what next? It turns out that in higher dimensions, this is the only equation satisfied by the F vector of every polytope. Okay? So if you want to study 10-dimensional F vectors, this is the only equation they satisfy. That's a fact. Yeah?
Can we at least get one direction on that arrow for higher dimensions? Like, say that all the edges have to be, I guess, hang on, let me formulate this. That all the faces of one certain dimension have to be at least the number of faces of a higher dimension.
So certainly there are results in this direction that if you have this, then you can conclude something. But the reverse is what's hopeless. To fully classify it is what's hopeless. But it is true that for an arbitrary polytope, you can say some things about the F vectors. Okay? But it's just not as elegant, because the reverse, a complete characterization just doesn't seem to exist, really. But then it turns out that, so like we do in mathematics, when a question is too hard, we think of an easier one and we solve it. Okay? And that's exactly what we're going to do. And what people in this theory decided to do was study the F vectors of simplicial polytopes. Simplicial polytopes, remember, are the ones where every face is a simplex. Simplicial polytopes are still a lot of polytopes, you realize. And it is one of the big accomplishments of this theory that F vectors of simplicial polytopes are fully understood. So somehow if you just add this extra condition, then all of a sudden the question is manageable. So we focus, I'm not going to say we because we're not going to say too much about this, but focusing on simplicial d-polytopes, a full characterization exists. So a full characterization of the F vectors of simplicial polytopes exists. And this is known as the G Theorem of Bilera, Lee, and Stanley. Okay. Again, another nice topic for the project and a harder topic for the project. It turns out that there's two directions. So Bilera and Lee proved that certain conditions were necessary, and Stanley proved that they were sufficient. And Stanley's proof actually was a pretty spectacular achievement in the theory because he just brought in this heavy machinery from algebraic geometry, and he used the Hard-Lefschetz theorem for toric varieties, and that's how he closed this proof. There are simpler proofs by now, but it is a hard theorem, a beautiful theorem, and I want to just give you an idea of just the beginning of what this theorem says. Okay? So let's start with a simpler question, which is what linear equations, what linear equalities do these F vectors satisfy? Okay. So if you are the F vector of a simplicial polytope, what linear equations do you have to satisfy? By the way, let me make an easy comment, which is, of course, that if you understand the F vectors of simplicial polytopes, then you understand the F vectors of simple polytopes, because we know that simple and simplicial are dual concepts, and we know that the F vector of a polytope is the reverse of the F vector of the dual, because vertices become facets and so on. So we know this for simplicial or for simple polytopes. Okay. So let me show you something kind of miraculous here. Let's consider this simplicial polytope, okay, the octahedron. And let's write the F vector So there's one empty set. There's 6 vertices. There's 12 edges, and there's 8 two-dimensional faces. Right? So this is the F vector. So I'm going to do something kind of strange. I'm going to do something that's kind of like a Pascal's triangle, but different. So this is going to be the right side of the triangle. The left side of the triangle is going to be a bunch of 1s. And then this triangle is going to satisfy that if A is B here and B is here, then A plus B is here. Okay? So here I get 6 minus 1. 6 minus 1 is 5. Then 5 minus 1 is 4. So you see, it's like Pascal's triangle, but each number is the difference of the 2 numbers above it. Okay. 12 minus 5 is 7. Okay. And then finally, the bottom row is going to be 1, 3, 3, 1. Okay. And I stop there. Okay. So from the F vector, I get this thing, and this is called the H vector. Okay. And clearly, if you know the F vector, you can reverse this, right? You know, if you take these guys, then you put 1s, and then you start adding in that way, like a real Pascal's triangle, and you're going to get the H vector, the F vector. So from the F vector to the H vector, they're kind of the same thing, but just a little encoding of the same, different encoding of the same information. Let's do this for another simple 3-dimensional polytope. Simplicial, sorry. We want simplicial, not simple. I think I said simple, but this guy is not simple, right? Because these vertices have degree 4, but it's simplicial because every face every facet is a triangle. So let's do this for the icosahedron now. So what's the F vector of the icosahedron? Well, there's 1. How many vertices does it have? 12. How do you remember this? It's the dual of the dodecahedron. And the dodecahedron has 12 pentagons. So this guy has 12 vertices. I never remember how many edges there are, and how many facets are there? 20. And then how do we figure out how many of these there are? Because we have Euler's relation, right? So what is it? $30 by 30? Because faces minus edges plus vertices should be 2. So 30. Okay. So that's the F vector. Okay, now let's do again this Pascal's triangle business, this kind of reverse Pascal's triangle. So 12 minus 1 is 9. 30 minus 9 is 21. 9 minus 1 is... You shouldn't be letting me do this in public. 12 minus 1 is 11. 12 minus 1 is 11. I don't even know where I got 9. 30 minus 11 is 19. 11 minus 1 is 10. And then the last row is going to be 20 minus 19, 1. 19 minus 10, 9. 10 minus 1, 9. So you see what I'm trying to tell you here. The fact is that no matter what simplicial polytope you start with, you're always going to get a symmetric vector here. Okay. Okay, so now let's say this in equations. Maybe we'll go over there. It's a very good question. So let me first define what it is. So definition, the H vector of P is defined to be the kth entry is equal to fk minus 1 minus okay, so that's something. That's something kind of messy, right? But the point is that the kth entry of the H vector is some combination of the F vector. Whatever the combination is maybe not so important for understanding what I'm doing here. But what I claim is that this formula exactly expresses what I did over there. Yep?
What's your last indice on that F?
F sub minus 1. Which, remember, is the minus 1 dimensional faces, which is the empty set. So this is a 1. Okay. So what I claim, and I'm not going to prove it because I don't know, I would make a mess, and it's just something that you have to compute. You call these f minus 1, f0, f1, f2, and then it should be clear to you that each one of these things is a linear combination of these, right? This is f0 minus f minus 1, f1 minus f0, f2 minus f1. And then these are some other combinations. And so when you do this, it's clear that everything here is some combination of the f's. And if you do it carefully, you see that that's exactly what it is. Okay? Okay. So why is this a nice definition? Because the theorem is that if P is simplicial, if P is a simplicial d-polytope, then hk is always equal to hd minus k. Now, to your question, what is the H vector really? There is an answer that is not so immediate to tell you, but there is something called a. Actually, maybe some of you went to this talk about shellings, and there's a notion of shelling, which is kind of taking a polytope and shelling it apart like an egg. It's really, the word really comes from taking the shell off of an egg. So if you take the polytope and then you start peeling off the facets like it's an egg, then these numbers have a meaning with respect to that process of shelling. Another nice project topic. Okay. But I think the point is that this is a beautiful way of encoding the F vector so that you can say this property really nicely. Because if you try to write this property in terms of the F vector, it's very messy. But from this point of view, it's very clean, it's very clear. Okay? So this is known as the then-Somerville relations. Okay? And you should realize that this is giving us d over 2 different equations satisfied by the F vector. Right? Because each one of these things is a combination of f's. So this says some combination of f's equals some other combination of f's. Okay? And so what we're saying here is that the F vector satisfies d over 2 equalities, linear equalities, okay? Which is which is, I think, very surprising, and especially when you write it like this, it's very clean. So, for example, given a three-dimensional polytope, if I tell you that it's simplicial, then what information do you need to know the h vector, to know the f vector? You don't really need to know anything except for this first number, right? Because this is always a 1. So as soon as I tell you what this number is, then you know that this thing is symmetric, and you'll be able to tell me the f vector. So that means that the f vector of a three-dimensional simplicial polytope depends only on one number. You just tell me what this number is, and I know the whole vector. So that's really the content of this theorem, that even though the space of f vectors should be d-dimensional, it turns out really it's only d over 2-dimensional. Okay? And
So is the algorithm to recover that first number?
I'm sorry?
Is the algorithm to recover that first number an easy thing to do? Keep that first number? Like given some sort of linear inequality or whatever for your polytope, how would you recover that number? How would you get it?
I think so the question is how would you recover this number? And I think the easiest thing would be to shell the polytope and count what that counts. So the fact is also that these are the only linear relations. Okay, so if you want to know what linear relations are satisfied by these f vectors, then it's these d over 2 relations and no others. Okay? These are all the relations. All the linear relations satisfied by the f vectors of simplicial polytopes. Okay. And they're independent, which when you see it like this, it's kind of clear. Yeah. Are there nonlinear conditions? Yes. So it's just like in the three-dimensional case for three-dimensional polytopes, we have one linear equation and two inequalities, which are linear inequalities. If you want to understand the full classification of the f vectors of simplicial polytopes, then you have exactly these d over 2 equalities, and then you have these other stranger inequalities, and they're stranger because they're not linear, but they're just some other kind of inequalities that are they're a little bit complicated, but they're very pretty actually. But so yes, there are other conditions. Okay. So what I wanted to do then for the rest of the class is give you an idea of how you can prove this, okay, which is some kind of generalization of Euler's relation using Erhard theory. So I'm going to give you a sketch of the proof of this. Okay. So the step one in proving this inequality, proving this equality, is just to unravel it, okay? Because this is a very compact thing, and the first thing you do is uncompact it by just writing it out. So you can translate these equalities to the following. So this takes a bit of work. This is not a trivial step, but it's kind of a step of doing some combinatorial calculations. I mean, you hk means something, hd minus k means something. You take those big equalities, and then through a bit of clever manipulation, you just make them look like this. Okay? And you prove that proving these inequalities is the same. These equalities is the same thing as proving these equalities. Okay? So that's step one. Now, what I'm going to do next, so this is what I want to prove. So let me rewrite this as, this is going to be a little bit strange for a second, but let me write k minus 1 as d minus 1 minus d minus k. And let me write I minus 1 as d minus 1 minus d minus I. Okay? And now let me write I as d minus I and k as d minus k. There's a method to what I'm doing here. d minus I, d minus k. Okay. You might see what I'm up to. What I'm trying to do is eliminate I and k and put everything in terms of d minus I and d minus k. And I'm almost done, except that here I have a summation for I from k to d. So instead of doing that, let me say that d minus I is going from what to what? If I goes from k to d, then d minus I goes from d minus k to d minus d. From d minus k to 0, but we like to write things in order, so from 0 to d minus k. Okay. And forget about this, and forget about this. Okay. Well, clearly the next step is going to be to give these things names. So let me call A equal d minus k. And B equal d minus I. So this goes from B. So A is d minus k, and B is d minus I. So I get B from 0 to A of minus 1 to the B, then d minus B, choose d minus A, F sub d minus 1 minus B. Okay? So I'm just kind of manipulating everything. And the reason I'm doing this is because I want to go to the dual polytope now. So if you have a phase of dimension d minus 1 minus a in the polytope, that corresponds to a phase of dimension a in the dual polytope. Okay. So this is the number of eight-dimensional phases in the dual. And this is the number of b-dimensional phases in the dual. Okay? So the point is that instead of proving this equality for simplicial polytopes, I prefer to prove this one for the duals of them, which are simple polytopes. Okay. This is what I want to prove. Okay. So that's what I'm going to do. So let's say that Q is simple. Okay? And let's take a phase of Q. And I'm going to repeat the previous argument and say that the Euler polynomial of this guy, so again, I'm assuming that this is an integral polytope. The Euler polynomial of this guy is the sum over the faces of f of the interior Euler polynomial of these guys. And then I'm going to use our hard reciprocity to get this. Okay? I have to do this a little bit quickly. So let me now take this equation and sum over all faces of dimension k. So then I get sum over faces of dimension k, and then sum over g a face of f, and then this thing. Okay? And now what I'm going to do, I'm going to ask you to look up because I'm going to erase some things on the board. So the first summation is over f, second summation is over g a face of f. So I'm just going to reverse the summation and write the first summation over g and the second summation over f a face that is that contains g and has dimension k. Okay. So I just switched the order of summation between f and g. And the reason that I do this is that you see all of this stuff right here depends on g and it doesn't depend on f. So that means that I can take all this stuff and factor it out of the summation and just move this summation over there. Okay? So let me do that. So I'm just going to take this summation and put it out here. I take this summation and I put it out here. And now it's just summation of 1. There's nothing there anymore. Okay? And it's gone from here. Okay? But then the nice thing about this is the following. I can compute this purple number very easily. And why is that? Because if we look at the lattice of flats, if we look at the lattice of faces, I'm sorry. So here's the lattice of faces. G is somewhere. And now this summation is over the faces that are above G. So these are the things above G and at level K. Okay? At level K. So I'm summing over these guys over here. So in other words, I'm just counting how many things are in this interval. Okay? Now this is level D, and this is level dimension of G. But then what I'm going to say is, look, this is a simple polytope. And remember that in a simple polytope, all the upper intervals are Boolean. So this is just a Boolean poset. These are just the subsets of this set. And so the number of things in this level is just a binomial coefficient. What binomial coefficient? Out of the D minus dimension of G things, I'm taking level D minus K. Okay, because this thing is Boolean. And let me just rewrite all of this stuff. Okay. And then, if you look at what I have here, I have this equation. Which is starting to look like this. It's going to look more like this if instead of calling this K, I call it A. A? Yeah. So this is A. And then I'm going to do exactly the same trick that I did for the previous proof. I'm going to say, let's look at the coefficient of t to the 0. Okay? So if I look in the left-hand side of the coefficient of t to the 0, it's going to be a sum of 1s. How many 1s? Well, exactly the number of faces of dimension A. So the coefficient of t to the 0 in the left-hand side is exactly f sub A. And if I look here, and I take the independent coefficient, then the independent coefficient here is a 1. And then what I have to do is sum over the faces of dimension B, and I get minus 1 to the B, D minus B, choose D minus A, and I get that term f sub B times, because that's